In this video you'll learn how to use the difference quotient formula to take a function and produce another function that shows how to calculate its average rate of change over an interval. This is the same as its slope, the slope of the curve of that function over some interval on the x-axis. There are several different ways to write this difference quotient formula, and they all mean the same thing. They're all slope formulas. They all calculate rise over run over some interval on the x-axis. Sometimes we represent the width of that interval as delta x. That's one variable. Delta x is not delta times x. Sometimes for simplicity we just use h, but it means the same thing. All of these formulas are slope formulas. They're just rise over run, the difference between the y values, or the vertical component, and the horizontal component, the x values. To give you a visual picture of what we're talking about with the difference quotient, let's recall the data that we were looking at last time. We had nuclear weapons testing data that's given to us as an annual rate. So this spiky graph at the bottom shows the rates of weapons testing every year throughout the world. Then the top graph gives us the accumulation of those. So this is the total number of tests that have ever been conducted. So we can find the average rate over an interval in two ways. First we have to pick the interval. And to do that we would start at some point and we would end at some point. And in the terminology of the difference quotient, where we start is going to be the x value, and then the width of that interval will be h or delta x, depending on which notation we're using. And that interval is the same no matter which graph we pick here. Then, as you know from before, we have two different methods of finding the average. We could either use the rate data, in which case we're looking for the line that best balances the stuff above the line with the stuff below the line, so it cancels out, and that level right there would be the average. But in this case, when we use the difference quotient, we're thinking about the graph, the function, as a kind of accumulation of rates. And so what we're looking for is to calculate the same number, but it will look like a slope on this function. And we know how to calculate a slope. We take the rise, that's the difference vertically, divided by the difference horizontally, and that's exactly what the difference quotient does. So when we find the slope, we're finding rise over run. The rise is the difference over that interval that the graph makes vertically. You see, at the beginning of the interval it's this high, and then it rises up to this high. So that's the rise, or the delta y, the difference in the function. And the difference horizontally is just what? It's the width of that interval, which we already have a name for. We're calling it delta x, or we're calling it h, one of those. So we find the rise in the function, and we divide it by the width of the interval, delta x, or h. So let's take a very simple function to start with. If we look at 3x plus 1, that's the formula that describes function f here in my problem. And what we want to do is use the difference quotient formula that will give us a way to calculate average rates of change of that function. All that probably sounds very abstract, so let's take a look at a picture. First, anytime you have to deal with a new function, I suggest you generate a quick graph of it to see what it looks like. You can do that easily with Wolfram Alpha. X plus 1, it'll do all the work for you. It shouldn't be a surprise that f of x equals 3x plus 1 is a line, and that its graph looks like a line. From what we know about lines is that they have constant slope. So whenever we use the difference quotient formula on this, we should expect to find that the formula is going to tell us that this function always has the same slope. Here's the formula using the delta x notation. So if we imagine wanting to find the slope over an interval x to x plus delta x, then this formula, as we described, gives us the difference in y's on the top, the difference in the function values, divided by the width of the interval, which is the difference in the x values. So all of this part of the formula is the f of x plus delta x. Then we subtract from that the original function. And then we divide by delta x. At this point we have some algebra to do. This 3x is going to cancel that 3x, and the 1 is going to cancel the minus 1. So all we're left with is 3 delta x divided by delta x. Well, the delta x's are going to cancel too, and at the end what we are left with is simply 3. So the average rate of change for this function over any interval that we might pick is just 3. We should have expected that because the original function was f of x equals 3x plus 1, which is a line with slope 3. The line always has a rate of change of 3 no matter where we are. Let's take a look at f of x equals x squared. This is a parabola, and I've inserted its graph here from Wolfram Alpha. And we're going to apply the same method to try to find a formula for its average rate of change over some interval. Unlike a line, the average rate of change will be different depending on which interval we choose. For example, if I chose this interval here from 0 to 1, the average rate of change would be represented by the slope of the function over that interval, which looks like that, the steepness of that line. On the other hand, if I pick the interval from minus 1 to 1, so my x would be negative 1 and my delta x, or h, the width of the interval, is 2, so the average rate of change would actually be 0. You started here, you spent half your time going down and then half the time going back up to end up just exactly where you started. So on average, your rate of change is the average of all those negatives with all the positives, which is 0. And in this case, the output of our formula should show that the slope of that line is equal to 0. So here's the difference quotient formula again with the delta x notation. Now f of x is x squared, so we plug in x squared into that and we get x plus delta x squared minus f of x, which is x squared, all over delta x. Then it's our job to simplify that. When you square something plus something, you have to use distribution or the FOIL method, whatever you've learned. So you should stop and verify that when you multiply x plus delta x times itself, you get this part of the numerator, x squared plus 2x delta x plus delta x squared. As in the last example, some of this is going to cancel out. The x squared and the minus x squared cancel out, and that leaves us with 2x delta x plus delta x squared over delta x. Both of those terms have a delta x, which we can cancel, and we're left with a very simple formula, 2x plus delta x. So this formula tells us for any x, that is a starting point on the x-axis, and any delta x, that's the width of our interval, what the average rate of change of the function f of x squared equals x squared is over that interval. If we chose 0.5 as x and 0.5 as the width, delta x, of our interval, then on the x-axis the interval looks like that. When we plug 0.5 and 0.5 into our formula, it will tell us the slope of this line, which is called the secant line that connects the dots, or the function value there and the function value here. The slope of that line is the average rate of change over this interval, and it would be 2 times 1/2 plus 1/2 is 1.5. If we let delta x become smaller and smaller, so the size of this interval shrinks, instead of a width of 0.5, if we choose something smaller, and imagine it getting very tiny until it's this microscopic dot here, h or delta x is very, very small. If we imagine it actually becoming 0, what we're left with is 2x. This is the instantaneous rate of change of our function at a particular point. That's the slope of the tangent line at the point x. And we call that the derivative of f of x. In math notation, we would write f prime of x equals 2x. To summarize what we've learned so far, if our function f of x is 3x plus 1, then its derivative is 3. And if the function is x squared, which I've denoted with a little caret there, x caret 2 means x squared, then its derivative is f prime of x equals 2x.